Recently, a group of researchers from China and Germany used AI to create quantum entanglement swapping protocol in a new way, where physicist Mario Kren and his team developed PyTheus, an AI algorithm that works as quantum experimental planner, and they can learn about quantum systems and plan quantum experimental protocols. Those researchers trained PyTheus to reproduce established or already known quantum entanglement swapping protocols. However, instead of giving and spitting the default method that has been trained on, it gives new method for quantum entanglement swapping protocol, which has less overhead than the one that has been used to create such experiments. This discovery opens the door to realize new ways of controlling quantum systems with AI. Will this open the tesseract of quantum computing advantage? In this episode, we will explore the origin of quantum information, how we can process quantum data, and how we can use quantum information to compute with quantum computers. We will discuss the challenges of quantum computing and how AI can help in advancing quantum computing on both theoretical and practical levels. Before we start, I like the scene of Interstellar movie about the quantum data in a black hole. The main actor, Cooper, falls in a black hole and finds himself in a tesseract, a four-dimensional space that allows him to see the past, present, and the future of his daughter's room. This scene is a sci-fi metaphor for the concept of quantum data, which are used to conclude the information that's stored in quantum systems. Information is an essential part of our life. It is the key to our understanding of the world around us. It is an extraction of data around that is processed and analyzed to provide meanings. From the smallest biological signals in your cells to the largest systems like weather patterns or social networks, information is a fundamental concept in the field of quantum computing and quantum mechanics. The problem is, we need to agree on how we define the information. Information is a result of processing data according to certain rules. It could be a physical model or some physical rules. It could be a representation as well. When it comes to information in the universe, we have the data. We could extract the information about gravity, electromagnetism, and other forces just by observing the data and processing it and develop a model that explains the data and convert it into information. But when it comes to computing, we need to control the system. We need to be able to control it. We need to map our representation of the data into the physical system that can be controlled and be manipulated as well. We need to be able to obtain the information from the system and translate it to a result that we can understand and we can comprehend. For example, analog computing was the first form of computing. It is deeply rooted in history. Early examples included the Antikythera mechanism. It is an ancient Greek analog computer used to predict astronomical positions and eclipses for calendrical and astrological purposes. Second example, astrolabes, which were used for solving problems related to time and the position of stars. And many other examples like slide rules. Those are examples of analog computers. The analog computer is a device that uses continuous physical variables to represent information. This is unlike digital computers, which represent data as discrete numbers, for example, zeros and ones. Analog computers use continuous values like voltage, current, or mechanical movement to represent and process information. Examples could be a chip that performs y equal x squared function, and this could be composed of a series of transistors or operational amplifiers that can be or that are connected in a specific way to perform such calculation. Analog computers were used to solve differential equations and other mathematical problems. They can perform complex calculations and operations, but they are limited to their precision and accuracy. The analog computer was eventually replaced by digital computer, for obvious reasons of course, which uses discrete values to represent information. However, they are still present in some applications like signal processing, control systems, and scientific instruments. They are also used in quantum computing, where analog quantum systems are used to represent and process quantum information. We'll see this part later. Now we come to the second example, digital computing or digital classical computers. Digital computing is the most common form of computing today. It uses binary digits, zeros and ones, to represent the data and process information. The basic units of information in digital computers or digital computing is the bit, which could have, in principle, one of two values, either 0 or 1. This could be represented by voltage levels of a transistor or a switch that's being off and on, and the on situation represents the 0 and the off is represented by 1. Typically, those bits are grouped into bytes, typically about 8 bits, which can represent a wide range of values, including characters, numbers, and instructions. Hence, to express a number with bits, we need to use binary representation, which is a series of bits that represents a number in binary form. A binary number is a string representing a sequence of zeros and ones that encodes the data. The data is processed by a series of logical operations which manipulate the bits according to certain rules. The result is a new binary string that represents the output of such computation. For example, the binary number 1011 represents the decimal number 11, as we see in the following table on the screen. Digital computers are based on principles of Boolean algebra and logical gates, which allow them to perform complex calculations and operations, translating what we wanted to do in our mind, and we write it on a paper, and what we wanted to do with it and how we want to compute it on a computer. This allows digital computers to perform complex calculations that we cannot comprehend or we do mentally or by a pen and the paper ourselves. But now coming to quantum computing, quantum bits or qubits are the basic units of information. In 1980, Paul Benioff proposed a quantum mechanical model of Turing machines. His work was based on a classical description in 1973 of reversible Turing machines by physicist Charles Bennett. In 1982, Richard Feynman published a paper titled Simulating Physics with Computers, where he proposed the basic idea of quantum computing. He suggested that quantum systems could be used to simulate other quantum systems in much more efficient way. He argued that classical computers are fundamentally inefficient to simulate quantum systems due to the exponential growth of information required to describe them. He proposed that a computer based on the principles of quantum mechanics would be able to overcome this limitation and efficiently simulate quantum phenomena. For example, it will be natural to simulate quantum systems like molecular structures and other molecular systems using such computer that leverages the principles of quantum mechanics. Leaving the paper of Feynman and coming to 1985, David Deutsch proposed the concept of a universal quantum computer, which can perform any type of computations that can be done on a classical computer. Deutsch argued similarly to Feynman that classical computers are limited by the laws of classical physics, resulting in an exponential growth of information required to represent the physical quantum system. His paper laid the foundation for the field of quantum computation by formally defining a quantum Turing machine, a theoretical model of a quantum computer, and demonstrating its ability to perform any computation that a classical computer can do. Of course, the idea of using quantum systems to compute with, or quantum computers, just kept evolving with time. And there were many proposals and ideas on how to use quantum systems to perform computations or develop what we know now as a quantum algorithm, a way to perform computations on quantum computers. However, there was no successful quantum algorithm that could be executed in a quantum computer until it was 1994 when Peter Shor and Love Grover proposed the first quantum algorithms that could outperform classical algorithms. Mainly Shor's algorithm for factoring larger numbers and Grover's algorithm for searching unsorted database. Before we move further, let's now define quickly what we mean by a quantum algorithm. A Quantum algorithm is a set of instructions that could be executed on a quantum computer to perform a specific task. It is similar to a classical algorithm, which is also a set of instructions that could be executed on a classical computer to perform a specific task. However, a quantum algorithm takes the advantage of the unique properties of quantum systems, such as the superposition and the entanglement, to perform certain calculations and operations much faster than classical computers and the classical algorithms. But before we dive into quantum algorithms, let's understand how we can load information first in qubits and how we can perform computations in quantum computing and how this could be used to execute instructions of a quantum algorithm to perform certain computations or certain simulation. Hence we come to the quantum data and the quantum information. The basic unit of information, as I have said earlier, in quantum computing is the qubit, which is the quantum analog of the classical bit. A qubit can exist in a superposition of states, allowing it to represent and process multiple values simultaneously. This property enables quantum computers to perform calculations and operations much faster than classical computers. The idea could be visualized in a Stern-Gerlach experiment, which is a simple experiment that demonstrates the quantization of angular momentum. The experiment consists of a beam of silver atoms that passing through an inhomogeneous magnetic field and striking a detector screen. Due to the presence of the spin of the angular momentum of the silver atoms, the beam is split into two spots on the screen. And this is a demonstration of the quantization of the angular momentum, which is a fundamental property in quantum mechanics. Prior to the detection, the atoms were in a superposition of the two states, mainly two opposite spins, spin plus half and spin minus half. And the measurements, when it performed, it collapses this superposition where the atom will end up in one state only that will be detected on the screen. So the measurement will be performed by the detector, and the detector, the interaction of the detector with the atoms when this collision happens, the whole wave function and the superposition collapses, and the atom ends up in one location representing the interaction with the field with one particular spin, or the spin positive half or the spin minus half. This sample of how quantum systems can exist in a superposition of states and how they can be manipulated to perform computations. Following this concept, we can define the qubit as a two-level quantum system that can exist in a superposition of states. This means for a qubit, for example, a qubit can have two distinct or two distinguished states, typically denoted as 0, Ket 0 and Ket 1, which correspond to the classical bits 0 and 1. Hence, a qubit is actually a classical bit if it is in the ground state or the default state. So it will be in the 0, will be described as 0. So this is described as a ground state. So it acts in this particular situation as a classical bit in the 0 state. Or it can act like a classical bit in one state when it becomes excited. The key difference here between qubits and the classical bits is that qubits can exist in a superposition of these two states, which means that a single qubit can partly be in a state 0 and partly be in a state 1 at the same time as we see on the screen. This property allows qubits to represent and process multiple values simultaneously, enabling quantum computers to perform certain calculations and operations much faster than classical computers. The superposition of states can be represented as a linear combination of the basis states 0 and 1s, where the coefficients of the linear combination are complex numbers. Here is the thing, there is a big difference between what we call classical superposition and the quantum superposition. The classical superposition, when you interfere two waves together, you always measure the resultant amplitude of this wave. You can physically measure it. However, when it comes to the quantum superposition, when you perform the measurement, one configuration survives and the other one dies and vanishes. In that sense, a quantum superposition means that you have different configurations that coexist at the same time, but when you perform a measurement, one configuration only survives and the rest vanish. And this is different when it comes to the classical superposition, where when you can measure the interfered and the resultant quantity of the amplitudes, either destructive interference, constructive interference, or in between. But you can measure the superposition or the resultant between both. And this is a key difference between what we call classical superposition and quantum superposition. Superposition is a fundamental property of quantum systems that allows them to perform quantum computations. For example, given a qubit in the state psi equal alpha ket 0 plus beta ket 1, where alpha and beta are complex numbers, the probability of measuring the qubit in the state 0 is alpha squared, which means that you multiply the complex conjugate of alpha times alpha, and then you get the probability of finding a qubit in this particular state. Similarly, the probability of measuring the qubit in the state 1 is beta squared, as we see. Beta star, the complex times the beta, then you multiply them, you get the probability. The sum of these probabilities is always equal to 1, which means that there is always a physical particle or physical system that represents by this equation. So that means that the qubit is always in one of these two states when it's measured, and when you perform as a measurement many times, this probability gives you indication about how many times you will find the qubit in the state 0 and how many times you will find it when you measure in the state 1. This is a fundamental property of qubits, and this allows them to represent and process information in quantum computing in much more efficient way. Within the amplitudes alpha and beta, we can encode the information and that we want to store on the qubit. Another important property of qubits is the entanglement, which is an important phenomena when two or more qubits are correlated in such a way that the state of one qubit is dependent on the state of the other qubit. For example, if two qubits are entangled, measuring the state of one qubit will instantaneously determine the state of the other qubit, regardless of the distance between them. You can think of entanglement as a form of quantum correlation that allows a qubit to be linked together in a non-local way. To learn more about entanglement and what entanglement means, you can refer to my previous video on quantum entanglement titled "What Does Entanglement Actually Mean?" Having said that, it is important to say that realizing qubits in a physical system is a challenging task. There are several physical systems that can be used to realize qubits, such as superconducting circuits, trapped ions, and neutral atoms. Each of these systems has its own advantages and disadvantages, and researchers are actively working on developing new qubit technologies to improve the performance and the scalability of quantum computers. For example, superconducting qubits are based on superconducting circuits that can exist in a superposition of states. These qubits are manipulated using microwave pulses, and they are read out using microwave detectors. Superconducting qubits are one of the leading qubit technologies and are used in many commercial quantum computers, such as those developed by IBM, Google, Rigetti. However, realizing perfect qubits, when we call logical qubits, is still a challenge. Typically, we have two types of qubits: physical qubits and logical qubits. Physical qubits are the actual qubits that are implemented in a quantum computer, where logical qubits are the ones that we use actually in our understanding or the development of quantum algorithms. The difference between physical and the logical qubits lies within that physical qubits are prone to errors due to the noise and the decoherence of the quantum states, while logical qubits are error-corrected qubits, and they are basically perfect qubits that can tolerate errors and be used to perform reliable quantum computations. The experimental challenges of realizing logical qubits are still a major obstacle in the development of practical quantum computers. However, researchers now are actively working on developing new qubit technologies and error correction codes to improve the performance and the scalability of quantum computers. Google recently announced their new chip called Willow, which has 105 physical qubits and use an enhanced error correction code. I have covered this in one of my previous videos as well, titled Willow Quantum Processor, Revolutionizing Error Correction, Quantum Computing, Parallel Universes. You will find the link on the screen. Google's work, it's a nice step towards building a fault-tolerant quantum computer. However, we are still far from realizing a practical value from this chip in the way which is promised by the quantum computer or quantum computing to deliver. Having said that, let's come now to an important question: how we can store information in qubits and how can we perform computations in quantum computing? Let's recall that representing or loading information in a classical computers is done by setting the bits to zeros and ones. We express the data in binary form and perform logical operations on these bits to process data. For example, numbers like 1, 2, 3, and 4 are represented in binary form, which as 0, 1, 1, 0, 1, 1, 1, 0, 0. This is a binary string that represents the data as we see them on the table on the screen. When we come to quantum computing, we need to load information into qubits, which are the basic units of information in quantum computing. A single qubit is a two-level quantum system. In our case, it is a two-dimensional object that can be either 0 or 1 or in between, which means that it can be in a superposition of states. And this is, of course, could be represented as a superposition of 0 and 1 as we have seen earlier states, or a linear combination of these two states as we see on the screen. When we come to loading information into qubits, there is a bit difference from classical computing. For example, we can encode the data into the coefficients of the state, which its square is the probability of measuring the qubit in that state. So basically, we can store information inside these coefficients alpha and beta and load them there. But hey, we can also use multi-qubit systems to represent more complex data. Multi-qubit system can be used to represent more complex data, and it is called quantum register. Quantum register is a collection of qubits that are used to store and process information. To manipulate qubits state, we use quantum gates, which are operations that act on qubits to change their state. For example, we can prepare a qubit in the state 1 by applying the NOT gate. The NOT gate will flip the state of the qubit from 0 and make it 1. We can also prepare a qubit in a superposition of states of zeros and ones by applying a Hadamard gate, which will put the qubit in a superposition of zeros and ones. These gates, for example, are the basic building blocks of quantum circuits, which are a sequence of quantum gates that perform specific operations in the qubits. To load information into qubits, we need to prepare the qubits in a specific state that represents the data that we want to store. This can be done using quantum gates, which are operations that manipulate the state of the qubits. For example, if we have one qubit quantum computer, the qubit is initialized in the state 0, and we wanted to prepare the qubit to be in state 1. We can apply a NOT gate, which will flip the state of the qubit from 0 to 1, and so on. So to change the state of the qubit, you need your gates, and those gates will manipulate the state of the qubit and convert them or adapt them to the state that you are aiming for. And the state that you are aiming for should be proportional to the data that you are aiming to load into qubits. Let's see how. There are several schemes that could be used to encode informations into qubits. The first one is the basis encoding. In this scheme, if we have a number which we want to load into quantum or a qubit system, we can represent the number in the binary form, like the 0 or 1, for example, or 2 or 3 or 4 or 10. and load it into the qubits by assigning each bit of the binary number to a state of a single qubit in a given multi-qubit system. For example, let's look on how we can load numbers from 1 to 4 on a quantum computer. First, we need to convert these numbers from 1 to 4 to convert them into binary form. We can see them on the screen, for example, now in this table. And we can see that in total, we have 3 bits in our binary representation that we need to represent the numbers from 1 to 4. We can assign for each bit a corresponding qubit in the quantum register. Hence, we need a 3-qubit quantum computer in order to represent the numbers from 1 to 4. The quantum register in this case, with the following quantum circuit that we see on the screen, can be used to load the number 1 into the qubits, which will be 0, 0, 1, where the first and the second qubits are left without any operations. However, the third qubit, this third one, is flipped using the NOT gate or X gate that flips the qubit from 0 to 1. So only we need one gate that acts on the third qubit to encode the number 1 in this 3-qubit quantum computer. Similarly, for example, number 3 can be loaded into the qubits as 0, 1, 1, because this is a binary representation of the number 3. And we can have a quantum circuit that prepares the qubits in this state to represent the binary form of the number 3 as 0, 1, 1. This can just be applied by leaving the first qubit alone and applying the X or the NOT gate to the second and the third qubits. Another example of encoding scheme is amplitude encoding, where the data is encoded in the amplitudes of the superposition of qubit states. This is a powerful method that can encode a large amount of data into a relatively small number of qubits, but it can be challenging to prepare. Once we have succeeded in loading information into qubits, we can perform computations on the qubits just by applying quantum gates to manipulate the states in a way that we want to perform a certain computations. And hence we come to what we call a quantum circuit. How we can perform quantum computations quantum computer? Typically, after loading the information into qubits, we need to perform certain operations on the qubits to process the data, and this is done using quantum algorithms. And together, quantum gates and qubits are the building blocks of quantum circuits that are a sequence of quantum gates to perform a given computational task. Quantum gates also differ from classical gates in a sense that they can act on multiple qubits at the same time, allowing them to perform parallel computations. Also, they are unitary operations, which means that they are reversible and can preserve quantum informations as well. For example, we can see that quantum circuits that creates entanglement between 2 qubits on the screen. The circuit consists of a Hadamard gate that puts the first qubit in a superposition of states 0 and 1, followed by a CNOT gate, which is a 2-qubit gate that will do this or perform this entanglement step and entangling the 2 qubits. This circuit creates an entangled state between the 2 qubits, which is a form of quantum correlation that allows the qubits to be linked together in a non-local way. To learn more about what is entanglement, you can refer to my previous video on quantum entanglement titled "What does entanglement actually means?" Also, you can learn about an interesting protocol called quantum teleportation, and also you can check this in one of my previous videos, Quantum Teleportation Protocol Made Simple. Those links are on the screen and also in the description of the video below. Okay, so we have seen how we can load informations into qubits and manipulate the quantum states using quantum gates to manipulate and produce quantum information to perform computations. But how we can actually do something with qubits, quantum circuits, and the quantum gates? What we do is actually a typical example of a quantum algorithm, which is again a set of instructions that could be executed on a quantum computer to perform a specific task. Quantum algorithm should include a quantum register, a stack of qubits that are used to store and process information, and a series of quantum gates, as we see on the screen, that acts on the qubit and perform the computations and the operations. And of course, this includes measurement gates that measures the qubits to extract the results of the computations. And the more importantly, the post-processing steps that are needed to convert the measurement results into useful output for our computation or the ones that we need. For example, training a quantum neural network, solving a system of linear equations, or factoring large numbers. These are some of the tasks that could be performed using quantum algorithms. Typically, so far, we have well-known quantum algorithms that are used and recycled in many quantum computing applications. For example, the variational quantum eigensolver. It is used mainly to solve problems in quantum chemistry. Also, it is used to train quantum neural networks. Variational quantum eigensolvers are sort of hybrid quantum classical algorithms that are using classical optimizer to adjust the parameters in a given quantum circuit to minimize the energy of the system. This algorithm is used in many applications in quantum chemistry, optimization, and machine learning. And this minimal energy that is computed with a variational quantum eigensolver is corresponding to the minimum values that you are aiming for in your optimization algorithm or in quantum chemistry calculations, for example, to compute the ground state energy of a larger molecule that cannot be computed easily using classical computers. And to be able to use such algorithms, you will need to find a way to translate your problem and the classical solution to the way that variational quantum eigensolver works. And this could be done by translating your problem into Hamiltonian, and the solution of this Hamiltonian is correlated to the solution that you are aiming for. So you wanted to convert the classical solution into Hamiltonian and then transform this Hamiltonian into qubit Hamiltonian that's used on a quantum computer. You transform this qubit Hamiltonian then into a quantum circuit and then run this quantum circuit on a quantum computer. A lot of times, of course, to get the results every time via measurement. And in the last step, you wanted to map the output of this measurement to the values that you are looking for. Typically, the mapping of your problem Hamiltonian into qubit Hamiltonian is not simple, and it's tediously done by using, for example, digital mapping like Jordan-Wegener or Pravai-Ketyov transformation, or you can use the analog computing also approach, which is more efficient and faster. However, it is theoretically more complicated and challenging also to implement. We'll have a separate video about these topics, the difference between analog and digital computers. But now we come to this interesting part, how quantum algorithms can benefit from artificial intelligence. In a nutshell, given the current known quantum algorithms, we just can leverage them and use the synergy between such available quantum algorithms to perform computations for other applications as well, and develop quantum algorithms for applications that could be similar to the ones that are used for or as an extension to them. However, as we have discussed earlier, mapping the practical problem into quantum algorithm is a challenging task. You need to define the problem first, map the solution and the way you think of the solution into the physical quantum thinking by defining your problem and your solution, and project it into a quantum algorithm. And typically this is a tedious task, and it requires a deep understanding of quantum mechanics and the quantum computing. After, you need to construct the quantum circuit that performs the computations and run it on a quantum computer. Once you do that, you need to measure the qubits and extract the result of the computations and perform a post-processing to get the final results that you are aiming for. So through the mapping of classical solutions into quantum computers, we can end up with algorithms that requires large number of qubits and long depth circuits. Many quantum gates that need to be implemented to perform such computations, which are challenging to implement on the current quantum hardware and sometimes isn't feasible at all. So in that sense, the AI comes in handy, where AI can help in scaling the models to larger systems beyond theoretical reach. Not only that, but AI also can help defining new protocols that could be used within a quantum algorithm to perform a specific task in a much more efficient way. And here we come to the recent news which we started with in this episode. For example, AI helped in rediscovering the new way of creating a quantum entanglement swapping protocol, where a group of researchers from Nanjing University in China, and in collaboration with a group of researchers from Max Planck Institute for the Science of Light in Germany, were designing a quantum experiment to create quantum entanglement swapping between two independent photons in quantum communication networks. They demonstrated a new way to create quantum entanglement of two photons without any direct interactions between them or sharing any common past. This is interesting by itself. But however, more interestingly, the specified scheme of their work was discovered actually using PyTheus or PyTheus. This an AI-efficient automated design and discovery framework for quantum optics experiments. The algorithm of PyTheus was trained to reproduce or redriving established protocols like entanglement swapping protocol. However, instead of spitting or giving back the default protocols that they were using, the AI unexpectedly revealed a less overhead protocol to entangle two independent photons. This discovery opens the door to realize new ways of controlling quantum systems with AI. This is also a nice example of how AI can help in advancing quantum computing on both theoretical and practical levels. For example, by training AI tools on models of physical systems, we can scale those models to larger systems just simply with these AI tools. Also, AI can help in developing new procedures, for example, to perform simulations and computations in much more efficient way. A few weeks ago, NVIDIA CEO introduced the idea of universal function simulators, which are mathematical models that can learn and approximate any function. What AI does is creating this universal function approximator, or this AI twin, for a particular simulation of a quantum system. By training the model on different quantum systems and their properties, AI models can learn the behavior of the quantum systems and develop quantum algorithms that can perform computations on them and potentially scale them to large systems. Hence, AI can help in accelerating the development of quantum algorithms, for example, by approximating tedious quantum algorithms that are not even feasible to be performed on the current quantum computers, just by replacing them by much more efficient quantum circuits that can perform quantum computations in a much more efficient way. In such case, it will make use of the current available quantum computers in the NISQ era, the noisy intermediate scale quantum hardware, to perform computations that are beyond the reach of classical computers. And we now arrive to the end of the episode. If you like this video, please give it a thumbs up and subscribe to the channel for more videos on quantum computing and AI. Also, let me know in the comments below what you think about the role of AI in advancing quantum computing and how it can be used to help in developing new quantum algorithms. And so if you need any help to implement quantum algorithms or physical inspired AI in your cases, and also implementing chemistry or physics simulations, don't hesitate to contact me. I will be happy to help you, and we can work together to develop a tailor-made approach that leverages AI and the quantum computing for your use case. This could be done also by our startup, Molkit, which provides consulting services and software services that can help in combining AI and quantum computing as well. Thank you, and see you next time.